motion graphs and their slopes. This is the post-lab for our graphing motion lab. Okay, you guys should be familiar with the slope of a line. If we write the equation for a line in standard slope-intercept form, we see y equals mx plus b, where m is the slope. It's the rise over run, or in this graph, delta y over delta x. So for a motion graph, we're always going to put time on the x-axis. That's always going to be our independent variable. And then, depending on what we're looking at, we'll put displacement, velocity, or acceleration on the y-axis. Just some graphing tips. Remember to always include units along with the axis label for both the x and the y. And also include the scale along each axis. Okay, here's a displacement versus time graph for something moving with constant velocity. Okay, you'll notice here, that the slope is delta x over delta t, which, if you'll remember, is the definition of our average velocity over a time interval. So here you can see that the slope is equal to the average velocity, and the y-intercept is equal to your initial displacement at time 0. Okay, so the slope of a displacement time graph gives us the velocity. And here's that equation again, rise over run. Now, if it's not a constant velocity, if there's some sort of acceleration, the average velocity can still be found over a time interval, just by taking the delta x and the delta t. If we do have the line tangent to the curve, so the slope at that point for a given time, we can find what we call the instantaneous velocity. Okay, what about a velocity versus time graph? So this one happens to have constant acceleration. Okay, so you'll notice this one looks like a straight line, but this is velocity versus time. Here, the slope is delta v over delta t, which if you've read chapter 2.4 in OpenStax, then you know that that's equivalent to our average acceleration. Since in this case it's constant, the average will be the same as the instantaneous at all points. Okay, so the slope of a velocity time graph is the acceleration. This picture at the bottom shows that when acceleration is not constant, you can still find the average acceleration for a time interval. You may have to do this from a graph, but for the most part, when we start working with the kinematics equations that we will derive later on, we will always use constant acceleration in those. Okay, so we found in some of our graphs using the motion detectors that when we were accelerating, we got a curvy line for our displacement. So this is when you have non-zero constant acceleration and you have what looks like a smooth curve. So we'll see this more in our lab on Thursday. But here's a little bit of trick. This will help in math class too eventually. Okay, if the graph is concave up, like shown on the two pictures on the left, there is positive acceleration if this is the displacement graph. At any point, the slope is the instantaneous velocity. Okay, if the graph is concave down, then there is negative acceleration, and the slope at any point along that curve is still the instantaneous velocity. Okay, now sometimes we'll have motion that has multiple stages. You actually did this in the lab. So when that happens, you'll have different parts of the graph that have different types of slopes and different shapes. So here, looking at the position versus time graph first, the one on the top left in red. From time t equals 0 to about t equals 20, it's kind of a concave up curve. And then from time t equals 20 to time t equals 40 seconds, it looks like it's a pretty straight line. So maybe there's some constant velocity there. And then from 40 to 50 seconds, it's a concave down graph. So that means there's acceleration, and we'll get there, but from the previous slide, we know that the acceleration here will be negative. Okay, so let's compare that graph to the one next to it on the right, velocity versus time. So in that first stage, from 0 to 20 seconds, it looks like I have a positive velocity, and it's increasing. Alright, so that means I have a slope that's positive and non-zero for my velocity versus time graph in that same time period. During the constant velocity section of my position graph, I have constant velocity, so it's some positive number, but my slope is 0. There's no acceleration there. And then from 40 to 50 seconds, right, we said that I should have some negative acceleration, so that means I should have a negative slope on my velocity graph. And sure enough, we do. So looking down from the velocity to the acceleration graph, you can see that for the first 20 seconds, there was a positive value for acceleration. Then the next 20 seconds, there was 0 acceleration. And the last 10 seconds, there was a negative value for acceleration. And here, you can actually see that the higher the magnitude, the absolute value of the acceleration, the steeper the velocity line is, whether that's positive or negative, and the faster the curve happens on the position graph. So, you'll notice that the acceleration versus time graph is what we would call a piecewise graph in math. And in reality, we can't actually accelerate instantaneously like this shows here. It would really end up being a little bit smoothed out, and you'd get a little bit of a curve. It wouldn't be a perfectly vertical line. But for now, in this class, this will generally be good enough. If you have any questions, please let me know. Good luck on your post lab.